guess I don't even have to mess with the left-hand side. Clearly, glancing at it, you can see that it's an even function. Can you?
No.
Oh, really? No? Let me prove to you this. Can I erase this?
Yes.
To show that the inverse hyperbolic secant is even, I'm simply going to play around with the hyperbolic secant of this thing, and if I can show you, the reader, that this is nothing more than the hyperbolic secant of positive x, I've shown you that this is an even function, and therefore it has symmetry with respect to the vertical y-axis. Let's just play. I think this is nothing more than the following. But that's nothing more than this, interchanging these two terms. Ah, shoot, we're already there. Clearly even.
What do you think about taking the definite improper integral from negative to positive infinity on this?
Oh.
We should probably determine
I'm sorry.
whether or not it's convergent.
What's that?
We should probably determine whether or not it converges fast enough.
Well, I get a little nervous about converging fastness. I typically show that with a series.
Yeah, exactly.
And I think if this improper integral doesn't converge, we'll see it through the process of actually guiding the integral.
Okay.
So let's see if we can give it a shot. I really don't know. Any ideas?
That works.
Shoot. You know what? I didn't realize it. I just asked the 32 students because it's an exam, the last exam. Didn't I?
Question.
Oh, you're right. Maybe it wasn't an integral. It was just a limit. Yeah, it was just a limit. My apologies. I take that back.
Well, first of all, you need to treat those as two, because you're actually taking the limit of an integral. So you need two constants to represent that. And you need
I think one will do it. I think you're suggesting that this is equal to negative infinity to one constant of that stuff, plus this interval.
yeah.
But you guys, do you think I can just stop? I mean, instead of computing two integrals because of all the symmetry, can I do this?
Yeah.
But that's nothing more than this. Sorry, I can't do this if you're in Math 31. You haven't seen this yet. But, sorry, apologize. It's in this chapter, though. It's in this chapter you're in right now. When I'm bound as infinity, I can just convert this to a proper integral, so I can use all my tools of calculus, and just simply take the result as t increases up bound. And I think to evaluate this limit, I think I misspoke everybody. I think to evaluate this integral, not this limit, I'm probably gonna
Integration by parts.
oh,
Yeah.
I didn't think of that.
So are we going to do the fancy form of...
I think that would be really nasty.
Really?
To involve factors of x in there.
The fancy form of one just like regular secant? Because isn't the integral of secant multiplied by secant x plus tangent x over secant x plus tangent x?
It would work beautifully. I didn't even think you were going to go that direction, but that would work. How about another one?
Really?
What's that?
It would work for the function hyperbolic?
Well, because the derivative, it's based off the... Because you're trying to get a form of derivative so you can use that.
Shoot, you know what? It doesn't work.
No, it doesn't.
No, because when it comes to differentiating tangent, you get the sign change. But when it comes to differentiating hyperbolic secant, you do get a sign change.
Yeah.
Unfortunately. So it doesn't work. It does fall apart.
What if you put a minus in there?
Do you see it?
Are you saying because you don't get a sign change, you don't get a... Yeah, I think I see what you're saying.
So I can write it down.
Well, I was just doing it in my head because you have to take the integral, or sorry, the derivative of hyperbolic secant, which would end up with negative that.
Negative hyperbolic secant, hyperbolic tangent, which gives you a sign change within that sum upstairs.
Yeah.
and so that's why it falls apart.
Oh, okay, yeah, I see.
Anybody else? Oh, come on, you guys.
Because the thing that was throwing me off this whole sign change is like, well, wouldn't we just change the sign of the whole integral, but it's a sign change between
Correct.
two,
It's between the two terms, that's why it
Yeah.
falls apart. You guys really? You're right now.
Zero
As,
hyperbolics.
with
As-
e to the x's.
With the e to the x's. And I think I just got a 2 over e to the x plus r, hold it, plus, my apologies, e to the negative x,
Pull out a e to the negative x.
piece of cake. But as I pull it out, I'm gonna throw it in upstairs. So can't you just
U sub.
take the answer?
U equals dot dot dot.
Say it again.
U equals dot dot dot.
No.
Well, I was hoping you'd just give me the answer.
It would be
Tangent.
tangent inverse
Inverse tangent of,
Sinh.
e to the
how about just e to
x.
the x?
Yeah.
As x places in from 0 to t. Oh, but shoot, that's merely gonna give me a 2 times, the limit as t plays this game.
You only drop a 2.
Yeah.
Say that again?
First, line with e to the x's, there's a 2 multiplied.
Oh, I'm so sorry, my 2 disappeared, didn't it? So if you don't mind not to change anything here, I'll just pull it out. I didn't see it. But you guys, isn't this merely gonna give me the limit of the inverse tangent of e to the t? I gotta go slow. You guys are gonna make me do all the work. I feel so alone.
Oh.
Is that okay?
Mhm.
Okay, never mind. When I plug 0
No,
here, don't I get e to 0,
yes,
which is
yes.
1. But the inverse tangent 1 is.
Pi over 4.
Okay, now you're better.
Yeah.
Okay.
Then you've got one that's going to pi over 2, right? Pi over 2 minus pi over 4. Yeah.
Really?
Because he pulled out the e to the negative x on the bottom. So
It's all
e to the
good.
negative x times.
Where does I?
Yeah, he is just distribution.
So you guys, next time you go to a party, you
I will not be going.
get these How do you come up with pie? You can show them this.
This is like if you want everybody to avoid you at the party.
Yes. This is why my wife doesn't take me to parties.
So, does the pi force come from the inverse tangent?
Yes. Michael, let me show you. And you tell me if I'm going too fast. But when I plug this lower bound of integration in, I get e to 0 power.
Right,
But that's just 1.
right.
But the inverse tangent of 1 is an angle. In particular, the angle whose tangent is equal to 1. And if you look at a unit circle, that point on the unit circle associated with pi quarters radians has these 2 coordinates. And the tangent of this angle, you know to be the ratio of y to x, which is just 1. So pi quarters is the angle whose tangent is positive 1. That's why I immediately wrote down the pi quarters. For those of you who know me, do you see why I'm saying hyperbolics are just such a piece of cake? They really are, aren't they? I think you guys just got nervous because you haven't seen it before.
It would be nice if the book had a chapter on them.
Actually, it has an appendix.
It has an appendix, yeah.
It's extremely limited, and I don't even know if he does any calculus. Maybe.
No, not really. They just give you the answer.
Okay, so that's right. That was it. He doesn't do anything with the calculus of the inverse
Good
hyperbolics.
stuff in the Stewart book and that lot.
Yeah,
Math
Stuart was
lot.
better.
So we know our inverse trig derivatives, right? Do those apply to hyperbolic?
Sine.
Yeah. In fact, it generated most of them.
I know, so that's what I was saying, so they're pretty much the same.
Yes. Well, I should say the same because inverse tangent has root 1 over 1 plus x squared. The inverse hyperbolic tangent is 1 over 1
Oh,
minus
yeah.
x squared. I mean, there's similarities, they're not equal to each other.
So, a quick question.
Yes,
Why did you guys switch to that book from the Stewart book?
I wasn't on that committee.
Really?
It's basically just a way for teachers to be able to do My Math Lab, which is like automated grading and stuff like
Yeah.
that. It's,
If you use my math lab with this book, which I do not,
I think that was the main.
there is,
thing.
then you automatically get an ebook. We just got some really nice pictures with technology that I think some of the faculty are using in the classroom on the computer. I don't access it because I don't have my math lab. But, you know, for those professors using my math lab, they love it. And they say the benefits of the technology outweigh the deficits with what some of us are complaining about.
Okay, so, I think an important thing for us in 31 and 2 here, since we're doing a lot of integration, maybe you could show us the different forms that pop up of the inverse hyperbolics and how they differ from the inverse trigonometrics, how to
Yes.
recognize based
No,
on
I
the
see it.
signs
I see it.
what your integral is going to result in, either a hyperbolic function or a trigonometric function, because it's often just, you know, a sign change or something like that. They often look identical to the.
For the current 31 students, I know you just started this. Perfect way to evaluate this integral is to use a trigonometric substitution. I maintain you don't have to, because you can just state the answer. Somebody give me some function out here that has a quantitative derivative, is what you see in the integrand's position. Inverse sine.
Maybe you could write them as a squared minus x squared.
And if I had this, it simply translates to this.
1 over A.
That's an inverse, isn't it?
Yeah. X squared.
Oh, you said 1 over a?
Yeah, 1 over A.
That's with inverse tangent,
Yeah.
not with inverse sine.
Okay.
Okay, that answers my question.
So you're thinking this? Inverse hyperbolic. Inverse hyperbolic.
Tangent.
Good nothing. It's just inverse tangent.
Oh, inverse tangent, yeah.
Oh, sorry, I misspoke. I forgot to put the a in there.
Yeah, exactly.
So when it comes to sines and tangents, a's on the inside on both, but not on the outside with sines. You do with tangents.
What about
Doesn't make a
secants?
difference. Well, we'll do these first. Do these first. What about this? Yes, sir.
So we're knowing these answers just because it's definitions of this stuff?
I hate to say definitions, definitely not. We were actually proved that the derivative sign of x is that thing, so now I can get that. It was a theorem, not a definition. It's something I can prove. Do you want me to prove it? Because I can. And this is the same thing without the a's, it's fine. It's still an inverse tangent.
No, wait, yep. Yeah, minus. So
Alright, it's wrong, it's wrong. So how are you gonna fix it? Yeah, so Randall, you're asking recognition. It's just when I see a difference like this, I think of inverse hyperbolic tangent. Well, I do.
Yeah.
I think a lot of you don't. A lot of you sit there and say, oh, I'll make a trig sum. Or, oh, I'll commit to partial fraction decomposition,
You
whatever
know,
that is.
the other thing is, if you look in like your back of your book, whatever, like tables and integrals, you'll see this written, the answer to this integral written in a logarithmic form, the 1/2 ln. Yeah, so just know that both forms are equivalent, and in terms of a memorization or learning whatever, it's gonna be quicker to write tangent inverse, and it's gonna be easier to remember hyperbolic tangent.
And I think if you use partial fraction decomposition, you would have split this up into sum of two fractions. Each one generates a log. There's going to be a difference of two logs. You rewrite the difference of two logs to log or a ratio. You come up here, but if you understand your hyperbolic or inverse hyperbolic functions, you can just immediately state your answer. My goodness, is there a dx missing? Or shall I do it like the book? Oh, you guys are such experts. Why don't you just finish this up? What's that?
I said sign.
So like Randall said, it's a game of recognition.
It really is. 'Cause they look so similar, it can be very confusing.
Anything else you can think of? Michael?
For example, no, 3. How come there's an x over a, and yet in example 4, x? Like, what makes in the inverse tangent, what makes it where it's an x over a?
If I were to come in and try to value this integral out of thin air, I would have done this. I would have said, let's come in, take the variable we already have, replace it with something like, I don't know, maybe a tangent of theta. And I'll pay the consequence of my actions. Now, committing to the substitution, I think downstairs what I'm left with is nothing more than a squared plus, well, I'll put x's new name in. That would be a squared tangent squared of theta. Times my, I shouldn't say times my dx, but replacing my dx with this alternative name, I guess that's just an a secant squared theta d theta. But if you guys allow me to come in and simply replace or factor out an a squared downstairs, here's what's left over. It's just that, when it comes to that denominator, using one of my Pythagorean identities, I think I can immediately replace what's inside the parentheses with just simply a secant squared theta. Now I get cancellation all over the place. I'm left with nothing more than the integral of 1 over a, which is just a constant with respect to theta, and I'll anti-differentiate. And I'll back substitute. Oh, I gotta slow down. When you go there, and isolate theta, divide both sides by a, take the inverse tangent of both sides, and you get the inverse tangent of x over a. And that's exactly where it's coming from. And the reason why the sine function, or excuse me, the reason why example number 2 does not have a factor of 1 over a on the outside is because here there's no square rooting downstairs. I got 2 factors of a. Here there is square rooting. So when I pull out and only get 1 factor of a, it cancels with the 1 over here with the dx. Not one left over downstairs.
Today in class, Chuck gave an example of a trig sub where he used secant, and then after that he used a hyperbolic sub with sine h, and it went way smoother.
That's why sometimes you come across issues where if you know your hyperbolics, your life is a lot easier.
Yeah, my question is it always that case with secant?
No, it's not always the case.
It's not always
No.
that case? Okay.
Yes, sir.
We talk about like Euler's identity and what we can use it for, because I know that.
What to use Euler's identity for?
Yeah.
Ooh.
In terms of hyperbolic function.
Hyperbolics.
Oh, in terms of hyperbolics.
Combines hyperbolics and.
Trigonometric.
Yeah.
Are you referring to the trigonometric
Yeah, the
to
trigonometric
hyperbolic
version of it.
relationships?
Yeah.
It's essentially the same equation, except you have an I attached to your e to the x, it's e to the ix, e to the negative ix.
Wait, which identity?
And that gives you sine. Cosine is the same thing, except you have an I attached to the 2 at the bottom. If you remove all those i's, you essentially are left with hyperbolic function.
You mean this?
No, in fact, I've got the thing on it right here.
Oh, do you?
I should just show you. Here, just turn this back on. Yeah, this is really interesting. For you guys who haven't seen this, this is on the math department webpage. Is this thing projecting?
I can hear it slowing down.
Okay. So if you go to the math department webpage, go to math resources, and it's like a drop-down menu, and the link is trigonometric versus hyperbolic functions. I've got it right here. This will come up in a second.
The directed comparison,
Yes.
that's nice.
Yeah, there it is. So as you can see, let me focus a little bit. Everyone see that?
Mhm.
So as we can see here, cosine is defined as e to the ix plus e to the negative ix over 2. And as you can see here, cosh is the exact same formula, except these i's are not there. Sine, it's the same equation, except now you have an I attached to this 2 here, and then when you pull all the I's out of it,
So
you're left with sinh.
This is sort of like a lighter level of what I said earlier with the cosine of a plus bi. You're saying it's hyperbolic cosine of b minus ai?
Yeah, so this is really critical, and this results in a lot of trigonometric to hyperbolic identities that involve different rearrangements of the I's. So you can go back and forth between trigonometric and hyperbolic if you know those identities, and that can make our lives a lot easier in certain cases.
In DE, when you study differential equations, life is so much easier if, in a higher order DE, with certain types of functions, to commit to the hyperbolic functions facilitates the differentiation process greatly. So for those of you in 33, you're going to see that this semester.
Where did you get this?
This is, so you see how, or let me pull this down, you can see this right here. Sierra College Math Department webpage. So I believe it's under the math resources, and it'll say trigonometric versus hyperbolic functions. Just click on this. There's a back page to it if you guys want to see that real fast. This is more of the stuff. They do have a lot of resources. I've tried to print it all out because I'm trying to take advantage here. So as you can see, there's inverse relationships. Not on here are the trigonometric to hyperbolic identities that involve the different forms of i's. You can find those in like table of integrals or something now.
So do you guys mind if I slip out? I have kids to pick up.
Okay,
Well,
so.
thanks, guys. Let's
Yep.
Hey,
talk.
wait, before you go, so I asked the math question of the week last week. What forms of, in terms of conic sections, we know that we see like spherical conics all over the place, like the planets in the solar system are eyeballs, just everywhere. But where can you think of examples of other forms of conic sections in nature?
In nature? The way a flashlight beam hits the ground is a conic section.
No, I mean, just aside from man-made.
Oh.
I mean, we know that the planets move in elliptical orbits.
Yes, that's one.
Reflection of the sun, right, on surfaces.
No air resistance, the particles moving through space.
Well, last
Comets
week,
are hyperbolic
orbits, I was reading the news online, and there's a science project going on somewhere. I don't remember who was researching this, and they were researching the echoing of the Big Bang. And I heard this when I was in graduate school, and then I heard it was debunked, but now they're coming up with it again. Namely that they're thinking that at least the outer edge of the universe is in the shape of a hyperbolic parabola, a curve that kind of looks like this. Because if you take two-dimensional cross-sectional slices, they're hyperbolas. Or a cross-sectional slice this way is a parabola. Which is really cool stuff if that's correct, because what if you're really far away from each other in the universe?
The wormhole?
A wormhole could be considered nothing more than pulling this up a little bit closer and just connecting directly in a higher dimension instead of traveling through our universe.
So what if we're like towards the bottom, or like below the brow?
Yeah.
We just screwed it over like,
I don't even know where our galaxy is in this very great picture.
Teeny tiny dot right there.
So is that like supposed to be the shape of the universe, assuming assuming no gravitational effects?
No, I'm assuming there is.
Okay, okay, I was just curious if like that's just like what it naturally is, or if that's after, you know.
And you can even see the warpage of
Okay.
the shape.
Wait, so I see a 2D plane here.
A 2D plane?
Not a flat.
Oh, you mean you see a surface?
Yeah,
But it's in 3 space.
but how?
How?
Like where's, what?
I'm just saying, theoretical physicists are suggesting that the universe, particularly outer edges,
So
are this shape.
everything in our universe would be on this
On the saddle
surface?
shaped curve.
On the surface,
I said curve, yeah, you're right, surface, on the saddle shaped surface.
surface curve, yeah.
Oh,
Wouldn't that
not
be- oh,
in
okay.
it. It wouldn't be in it.
On it.
Floating in it.
On it.
On it.
And Randall, what a good question. I mean, I can sit here for hours and
Yeah.
talk about really cool
Yeah, and
applications,
that's why I
but they're
said-
man-made.
Yeah, I said, think about it and we'll collaborate next week, so.
I will do that.
That was
I will do
kinda-
that. Okay, all right.
Yeah.
You guys have fun.
All right, perfect. Thank you, Mr. Bell.
You